Thank you. And thank you everyone for tuning in to my talk. My name is Vrátil, and today I want to talk about C++ coroutines and Qt. I've been working with Qt for over a decade now. I actually learned C++ through Qt. And I always thought I knew C++ fairly well up until the point where I actually left my previous job and moved on to a new job where I don't use Qt anymore, and I use basically pure C++. And at that point, I realized, well, I don't know C++ at all. I realized what I knew was sort of the Qt dialect of C++, because, well, Qt has certain parents, right, of API that don't necessarily match or work well with whatever is the modern C++ thing. And so I found it a bit annoying that I wanted to use the latest, greatest features of C++ that I just learned, and it didn't always fit well with how Qt works. But nonetheless, I found a new hobby, and that's sort of learning new fancy C++ feature and then trying to see how to make it work with Qt, or if I can make it work with Qt somehow. And one of these latest sort of discoveries I made were coroutines. And I'm actually quite excited about that. And just considering by the number of talks on this very conference about coroutines, I think I'm not the only one who's excited about coroutines. And as I was learning about the coroutines, I figured like maybe this is something that would work with Qt very well. This is something that could solve some of the pain points that I see whenever I look at my Qt code base. Mostly when dealing, as more and more we deal with like asynchronous things, asynchronous operations, or you want to just wait for something to happen, right? And with Qt, the code tends to get a bit complicated. And well, I thought coroutines could solve that, so I started playing around with that, and the result of that is a library called QCoro that I want to introduce as part of this talk. I'm sure you are on this talk because you are interested in Qt and maybe coroutines. So I guess you know a thing or two about Qt. Still, just to make sure we are on the same page, I'll do a super quick introduction to Qt, just so we are all on the same page. Then I'll try to explain the problem I have with how we deal with asynchronous operations or sort of waiting for something in Qt. Then I'll outline the solution that coroutines and QCoro offer. And finally, I want to look a bit into what else we could do with coroutines in Qt. So as I mentioned, I just want to do super quick introduction into Qt, and I will only mention the two core things that really matter for this talk, and that's the Qt event loop and the signals and slots concept. The Qt event loop is just an event loop like any other. If you've never used Qt but used some other system that has an event loop, this is exactly the same thing. Usually you have a single event loop per thread. You can also have threads without event loop, but you can perfectly do it's perfectly valid case. What we don't like to do in Qt is nesting event loops. Event loops can be nested. Technically, it's possible. It's sometimes used to sort of like a hack to work around where you really want to do some when you want to block inside some function, but you don't want your UI to freeze, for instance. You still want to be able to dispatch events, even if you are not able to return to the main event loop. So you nest it. You create a nested Qt event loop. However, that's generally just a whole can of worms that can lead to all kinds of crashes and issues with. So let's just assume we don't want to do that at all, right? I mention it here because I'll show you some examples afterwards, and to almost any of them, or almost all of them, you could say like, well, I could solve this with a nested event loop. Yes, you could. I'm not mentioning that at all because in generally, you want to avoid nesting event loops. Signals and slots, that's sort of like something like a callbacks, but for Qt. Signal is just a regular member function. You as a programmer, you only declare it. You don't write the definition, the implementation. That's generated at compile time by MOC, which is sort of like a little tiny Qt helper tool. When you emit the signal, so you really just call the function. It's nothing. It's just a fancy name for calling a function. Qt then takes care of actually calling all slots that are connected to that particular signal. And what is a slot? Well, it's just a regular function. And whenever a signal that the slot is connected to is emitted, the Qt will make sure that the slot is called. The relation can be like M to N, so you can have multiple slots connected to a single signal, and you can have a single slot invoked from multiple different signals. The main difference between this and callbacks, like regular callbacks, is that the connection between the signal and slot can happen outside of the two objects, right? Outside of the emitter and the receiver, you can have a third party that just binds them together, which helps with separating concerns and untangling interdependencies. So that's just a super quick introduction to Qt, because we will see those two things. Well, I will mention event loop, and we will see some signal and slot connections all over the place. So that's how I wanted just to make sure that we all that we are all on the same page with this. So now let's look at the problem that I have with Qt and that I was trying to solve. In Qt, or well, generally in programming, right, we often deal with asynchronous operations like network requests. And when you do a network request, you obviously want to wait for the answer and then process the result from that reply. And the problem here is, how do you wait? What do you do? What should the code do while it's waiting, right? Should it run some other stuff? Should it run some other tasks, or should it just be blocked and wait until the reply arrives before it can continue? Or maybe should it just, continue doing some other things, like looping in the event loop, dispatching other events, and making sure that the whole application remains responsive? Depends, of course, on the application, but in all of those cases, you will always be asking yourself when you are writing the code, like, how do I handle this, right? And then you realize, oh, I also need to handle errors properly and error propagation, and the whole problem just gets more and more complicated. So let's look at an example that I have here. So let's have a simple function, or a simple member function, which is called Getusername. It's part of some API, class represents a remote API. So the function, if a function is called Getusername, it takes user ID, and I expect it to return the username if it's called Getusername, right? So this function takes a user ID and returns a Q string which contains the retrieved username. How do we do this? Obviously, in Qt, when you want to do a network request, you need to set up a Q network access manager, or it could be a member variable of the API service object. But to make those slides simpler, I made it this way. And then you call the network access manager.get, and you pass a Q network request there. The Q network request just holds the URL that we are actually sending the request to, and then maybe some additional headers and whatnot. And it returns a pointer to Q network reply. So perfectly fine. We jump here and we read whatever the reply contains. So we read the data from the reply, we interpret those data as our username, and we return that to the caller. Problem solved, right? Now the question obviously is, so if I fire a network request, I won't get the reply immediately, right? It will take a bit. So how do I wait? So obviously the most evil approach is just to use reply wait for ready read. So this is a function that blocks until there is something to be read from the reply, or it's actually from QIO device, but still. The good thing here is that this makes your code super simple to read, right? It does obvious things, and you read it from top to bottom. The disadvantage is that this function will actually block until the reply arrives. So there is no event processing. Your event loop is blocked. And well, this is not the ideal solution, right? Because if the username is really long, you might not have the whole username arriving in the single chunk. So the read all might not read the whole username, and then you get only part of username. So there would have to be some loop and so on. But again, for purposes of this slides, this is one approach, but obviously not the right one, unless we want to like have every single request running in its own thread or something like that. But then it makes it a bit more complicated again, since you need to handle like, how do I get the result from that thread? So how would we do it with more of non-blocking approach? So this is one of the possible approaches. If you look at the changes highlighted here, is that the signature of the function has changed. It now returns void, and instead it takes a callback, additional argument, which is a callback that will be invoked by the function when the reply arrives. And we use the connect here to connect the finished signal of the network reply to a lambda that we have created here. So when the network reply emits the finished signal, this lambda will get invoked by Qt. And what the lambda does, it just simply reads whatever has arrived from the server and forwards it into the callback, or it invokes the callback and passes the username to it. So the caller can then do whatever they want to do with that. So this is a fairly simple, straightforward approach that you might use in order to write a properly asynchronous network request, right? So this is sort of a typical, well, it's not that typical Qt, because in Qt generally using callbacks is not as common, I believe, or I would say, since the connect syntax, single slot syntax, is trying to replace the callbacks system. So this is an example of how you would use our get username function. So the code at the top that is highlighted right now, that's the first blocking case, right? So you simply call API service dot get username. It blocks for a while and gives you the username, and then you do something with that on the next line. This is what it would look like if we were using the other option with the callback. So again, we call get username, and we pass lambda as a callback, and when that lambda gets invoked, we do something with the username again. So the difference between this and that, the example above and below, is not that big, right? It is still fairly easy to read them and understand the code flow and what's going on. But this becomes more complicated once you start chaining those calls, right? Imagine, okay, so I got the username, now I need to ask another backend for something else, and it gives you some other result, and then you want to ask some other API endpoint to do something else with the data, and you sort of need to chain those requests. If you use the asynchronous approach, this quickly becomes messy, and things like error propagation becomes tricky, right? How do you actually pass an error back to the caller who called this whole thing? Probably the caller would have to pass you some callback as well that you would call here, and it all tends to become a callback hell that's really difficult to navigate. With the example above, it would just be a series, of you do a request, you check if it failed. If it failed, you return early, or you do next request and next request and next request. And you have the whole thing in a single chain of lines, which is super easy to read, and there are no hidden surprises or the code suddenly jumping somewhere else and then coming back. So that's what's good about the blocking approach. But obviously we don't want any blocking, so we might end up doing the other approach. So this is to sum up the pain points that I have. So that chaining code is difficult. Errors are hard to propagate, and the code gets hard to follow and hard to understand. especially if maybe you are not using lambdas everywhere, but if you implement maybe part of the callback logic would be implemented in a standalone function somewhere else, and then you need to realize, okay, so I'm jumping to maybe a different file or somewhere else in the file. And what I've seen in projects that I worked on, as people start adding more and more code, they sometimes put it in random places, so then you are jumping down, back, and really it's hard. The code becomes hard to maintain and read. So sorry, let's look at the solution that I think I found, and that's coroutines. So this is the example. This is sort of a combination of the two examples that we have before. If we look again at what has changed, that's the highlighted parts. So the return type of the function has changed. It's now QueueCorro task QString. What is QueueCorro task? Let's not care about that now. I'll explain that in a moment. What's important is you can see the QString type there. So in a way, you see that the function returns QString. Ignore that it's wrapped in something for now. And then there's the cool thing. What we do next is how we execute the request. This really is similar to the first case we had, the one that blocks. What happens here is the network access manager.get creates a QNetwork reply, and the QNetwork reply gets passed to the CoAwait keyword. And the CoAwait keyword does magic, and out comes, again, a QNetwork reply, but this time the reply is already finished. What happens, the CoAwait, it checks if the reply is already finished. If it is not finished, it suspends the coroutine, it suspends this current function. And when a function is suspended, it chains up. So it goes back to the caller. The caller is very likely also CoAwaiting result of this coroutine. So it suspends as well because the result is not yet available, and so on, until we reach the event loop. And the event loop can continue happily looping and dispatching events. Once the QNetwork reply is finished, the coroutine gets resumed. So the CoAwait keyword, so the CoAwait, the code that is hidden behind CoAwait, let's put it this way, it gets triggered again and resumes from there, and it returns the QNetwork reply that it got on the input. But this time we know for sure that the QNetwork reply that we have in the reply variable is already in the finished state. So we can safely read all from it. And then at the end, we use coreturn instead of return because we are returning from coroutine, so it has to be coreturn. So what we got here is a code that's written in a synchronous manner, but in fact executes asynchronously without blocking our event loop. So your application remains responsive, which I think is really huge, or at least for me. This is basically what I described. So when CoAwait suspends the coroutine, the execution returns to the caller. If the caller wants the result of the callee, and the caller knows it's a coroutine, it will probably CoAwait on that callee. So it will get suspended as well. And you probably have this chain of coroutines up to the point where you reach a sort of a top level where your function, your coroutine, was invoked by the queued event loop. And the queued event loop doesn't care about coroutines. It just knows that, oh, the function that I just invoked has finished and returned, so I can continue doing my event loop stuff. So it gets unblocked. The tricky part is when it is supposed to resume again, because then the event loop somehow calls into the QNetwork reply. The QNetwork reply emits the finished signal, which then resumes the coroutine. So the call chain, if you looked at that in GDB, for instance, it becomes really convoluted because you have like two loops through the same event loop. Yeah, so that's that described. Next slide. There we go. So now to describe the QCoro task type that you saw as return type of the coroutine. Why do we have QCoro task? Why can't we just return QString? Well, that's because coroutines have to have a special return type that satisfies certain criteria. It means that the coroutine we have can be co-awaited by the caller. And as a part of the QCoro task, and that's the part that makes this whole thing work, is a promise type. In our case, it's QCoro task promise. And this is where the magic really lies, because if you think about it, we were co-awaiting on a QNetwork reply. And I was saying, okay, so the co-await, it looks if the reply is finished, and if not, it suspends the coroutine. And then when it gets finished, it resumes. And maybe, you know, like, how does co-await know what QNetwork reply is? Does the compiler magically understands Qt libraries? And the reality is no. The co-await keyword, or the code behind co-await, does a lot of stuff. There's actually, to my own surprise, there's a lot of code behind that single keyword that's being emitted. And one of the things that this code does, it looks for a function called await transform that's implemented on the promise type. And in case of QCoro, the QCoro provides, well, sorry, the promise type in QCoro, it has a special implementation of await transform that checks if there is a trait called QCoro detail awaiter type, for whatever reason. I called it this name. And if this type exists, it means that there exists a wrapper that is coroutine aware for that particular type T. So in our case, T is QNetwork reply. And the QCoro library defines a trait for QNetwork reply. And it has a wrapper called QCoro network reply, which is compatible or supports the necessary coroutine functions. So this is returned from await transform. So basically, what the QCoro task does, to sum it up, is it allows us to turn a type that does not support coroutines, like QNetwork reply, into a type that does support coroutine, like the QCoro network reply wrapper. And this type then can be co-awaited by the co-await. The cool thing about this is that this all happens, all of this stuff is basically hidden behind the co-await keyword. So there's a lot of boilerplate code going away. And I really like that, right? This hides a certain amount of complexity that you would have to copy and paste all over the place if it weren't designed this way. So this is something I really like about it. There we go. Okay. So this is an example of what it looks like, what the trait looks like. So it's like a template specialization for that particular type. In this case, it's QNetwork reply pointer, and it defines what the type that can perform a particular operation but supports coroutine is called. So in this case, we have QCoro await for finished operation. So that's just a class that simply gets, well, it looks like this. I have it on the slide, actually. So it looks like this. It's a class which is constructed. It takes the QNetwork reply, so it's like a simple wrapper class, really. And then it has the three key functions that are needed if your type is supposed to support coroutines. So that's await ready. This function is called by the co-await before it suspends the coroutine, just to check if it actually has to do that. Before going through all the loops and hoops of suspending a coroutine, the co-await first checks if it actually has to do that. So here we check if the QNetwork reply is not finished yet. So for instance, if we would pass a really invalid URL, the QNetwork reply that we get from QNetwork Access Manager would already be in some finished but invalid or error state. So there would be no reason, no need to suspend. However, if this function returns false, then the CoAwait goes on to call await suspend. So it suspends the coroutine, and it gives us a handle to the coroutine itself that is being suspended. And what happens inside this function is super simple. What we do is we simply connect to the QNetwork reply finished signal, and in the slot that's connected to the signal, we simply call awaiting coroutine dot resume. So in that slot, we simply just resume the coroutine again. So when Q calls our slot, when the network reply is finished, we simply resume the coroutine that's awaiting us. And finally, so when the coroutine is resumed, is awakened and resumed, the CoAwait extracts called this function, which extracts the QNetwork reply. The return type of await resume can be anything, right? So other option would be it could maybe return, it could actually do the read all inside, and it could return the Q byte array with the whole data. So you could just co-await the data directly. Although this makes it a bit, more, well, you can handle errors and things like that, right? So that's why we are returning QNetwork reply, but you will see that QCoro has a bit more to offer. So to talk a bit more about QCoro itself, it's a MIT licensed library that supports GCC, Clang, and MSVC. So it supports all three major platforms, so Linux, macOS, and Windows. Basically, to sum it up, it provides coroutine-friendly wrappers for various standard Qt classes. Those classes that are currently supported are QIO device, QProcess, QTimer, QFeature, QAbstract socket, and QLocus socket, QNetwork reply, QTCP server, and QDBus pending call and QDBus reply. Those are the supported types right now. Just by supporting QIO device gives you coroutine support for a wide range of QIO device, for basically any QIO device subclass. So for instance, the QProcess, which is also a QIO device subclass, means that we get support for something that's extra in QProcess, like waiting for the process to start and finish. But we also get all of, we can also co-wait on the IO device having data ready to be read and or ready to be written and so on. I'll show that a bit more in the upcoming examples. Another useful thing that QCoro has is awaiting signal emissions. So sometimes you may want to just wait for some signal to be emitted, and we support that with QCoro as well. Now, what we saw was co-awaiting directly the QNetwork reply. That is fine, but there are types, and QNetwork reply is actually one of those as well. But for some reason, I also decided to have sort of a default action. Certain Qt types, they have multiple operations that you may want to co-wait for. For instance, here I have an example from QProcess, which has wait for started and wait for finished function. So it makes sense to be able to co-wait both of them. But if I would just, to write co-wait process, well, process would be the QProcess instance, it's not clear which one of those is being awaited, right? So I'm waiting for it to start or I'm waiting for it to finish. So in those cases, there is a QCoro function, which is a function that is overloaded for all different kinds of Qt classes, or well, at least for the Qt classes that QCoro supports. And it basically just returns a thin wrapper class for that particular type. So for QProcess, we have a QCoro process. And this QCoro process has a bunch of functions or methods, and those are conveniently named the same as the methods on the original class, so as in QProcess. So QCoro process also does have wait for started and wait for finished. The difference is that those classes return awaitable types, while QProcess wait for started is a void function, I believe, or maybe Boolean. It returns whether it's timed out or not. the wait for started methods implemented in QCoro process, they return what I call operations. So like wait for started operation and wait for finished operation. And those types, they are co-waitable. They implement those three functions that we shown previously for the QUnit work reply. And the await resume function, the result of the co-wait expression, then of course returns the again true or false where it timed out. Now I noticed I have a mistake in my slides. I apologize. There's a CoAwait missing here. That should be CoAwait and CoAwait before the QCoro. Sorry for that. So you have started equals CoAwait QCoro process and so on and so on. So this wouldn't actually build. Sorry. This is another example. So this is an example where we use the code. So it's like we create a queue process and then we start GPG, which is like a encryption utility. And now we want to know when it starts. So we simply CoAwait for the process to start. So we call QCoro, which gives us the wrapper class, and then we call wait for started, which gives us the actual type, which becomes the waitable, and then we CoAwait on that. Next, we know that, okay, the process is started, so we can simply just write the data that we want to have that we have encrypted. So we have some encrypted data, we write them into like standard input, and then we close the write channel, which indicates to GPG that it can start decrypting. And then we just have to wait until the tool finishes. So again, we use CoAwait. And after that, we know for sure that the GPG has finished, and that we can safely do read all, because that means we get all the data now. So if we were reading before that, we might only get the first chunk of data, and then more could be arriving later. Now, if you look at this code, this looks absolutely synchronous, right? You would think like, okay, this will block my app until the whole decryption happens. But the reality is it won't, because we use CoAwait here, and this coroutine will get suspended in those two places. And so you can have this single function called decrypt, right? Which is, in my eyes, this is much simpler than like having to connect to started signal and then writing the data and in the slot for that, and then connecting to finished signal and then reading the data in that slot. I find reading this much more straightforward, especially as the code maybe grows more complex. Here's an example of awaiting signals. So let's create, just as an example, let's create a key object derived class called process monitor. And the process monitor will have a signal which is called process started, and it has a single argument, which is the name of the process that just started. And now let's just say that we want, this could be like a third-party library that for some reason you can patch it to make this coroutine friendly. And so instead you want to, but you still want to CoAwait that signal to be emitted. So the way you do it is again by using a special overload of QCoro, where you pass the object and the signal. So this is the same as the connect, so first half of connect syntax. And then you CoAwait on whatever QCoro returns. The cool thing about this is that the result of the CoAwait expression will be the argument to the signal, right? So this process started has a QString argument name. So here you receive the argument as a return value from the CoAwait expression. So you can also read the signal arguments this way. So again, makes the code much more easier to read in my eyes. Obviously, if you happen to have multiple arguments, then they are returned as a tuple. So you can simply use the tuple decomposition to receive it this way into the caller. So this is I think a nice way to wait for signals. Here is another example of a super simple server. So we create a TCP server. We say, okay, listen for incoming connections, and then we have like an endless loop, which really, if you like, okay, I never want to have this kind of construct in my main UI thread, right? This would just block forever. The cool thing about coroutines is now you can simply have this in one of your slots that you just make sure gets invoked from the event loop, and this will not freeze your event loop, and it will not make your UI freeze. Here, what we do is we co-await a new connection. So again, we wrap the server because a QTCP server has multiple operations that we may want to co-await for. So we have to wrap it in QCoro. That gives us the wrapper. We co-await for new connection. So this not blocks, but suspends until a new connection is available, or maybe forever if there are no incoming connections. And when we have the connection, we just, again, wait for there to be any data, again, by suspending, not blocking. And then we write them back and close it. So it's sort of like a simple ping pong server. And then we go on to wait for another connection. There is also acute concurrent support. So instead of having to wrangle with QFuture and QFuture watcher, you can simply just co-await the QFuture, which again makes suddenly, in my eyes, this suddenly makes using acute concurrent much more user-friendly, because I always hated fiddling with these extra watcher types. Same goes for dbus. Actually, I do not have an example of dbus, but if you ever use Qt dbus and you don't want to block or anything, you want to absolutely avoid blocking dbus calls, then you hardly avoid using QDbus pending call watcher. So you get the call, then you have to set up the watcher. You connect the signal slot, and then you have to not forget to delete the watcher. And again, with dbus, the syntax looks very similar to this. You can QCoro brings support for CoAwaiting QDbus types, like QDbus reply. So this actually happens automatically. So I am sort of getting to the end fairly quickly. I have some future plans for the library. I wrote it for the types in Qt that felt like sort of like, why don't they support it yet, right? Well, obviously because Qt doesn't allow C++ 20 yet, and I don't see how coroutines would come into the Qt API easily. But I picked those classes like, okay, those are obvious candidates for having supporting QCoro. But as I like sort of write more code elsewhere in Qt, or as I think about it, I'm always notice some new class that I say, oh, this one operation could be made into coroutine, so I could co-await it. So I would definitely like to introduce support for some GUI and widget classes, like for instance, waiting for dialog to complete and then or to be closed or accepted or rejected, and then returning the result actually as a return value of the co-wait expression. So that might be interesting. The library itself is split into modules that have the same name as the Qt module. So there's QCoro Core, QCoro Network, QCoro Dbus, and those are separated libraries. So you can actually just link the libraries that you use, and it doesn't unnecessarily pull in, like, if you don't use dbus in your application, it will not, you just link QCoro Core or QCoro Network, and it will not unnecessarily pull in, not just QCoro dbus, but also QDbus if you don't need it, or it's maybe not even supported on your platform. And another big thing that I would like to add, and that would really improve sort of compatibility with Qt, is for the QCoro task thing to be able to have to be a Q object, or have some other way to do that, to emit a finished signal. Because sometimes you may find yourself in a case where you are implementing a function, you are implementing or re-implementing some virtual function, some interface that was not created by you, someone else, and you can't change it. Maybe it's a Q abstract item model, right? And you're implementing data, and here you would normally you would say, oh, it would be amazing if I could just co-await some, like database fetch or whatnot. But you can't, right? Because Q abstract item model data is not a coroutine. You can't use co-await there because the return type is Q variant and not coro task variant or something. So in those cases, I would like to have some way where you can use the standard old school Qt style of simply connecting a signal to connecting a slot to some like finished signal of the task object, the object returned from the coroutine, and then your slot would get invoked later on. This, so far, I wasn't able to get it work. So, but this is something I would like to see, because really it would allow using QCoro even in code bases that are absolutely not ready for this, or a third party, or integrating right with third-party libraries and so on. Another thing that I started sort of digging into is truly asynchronous and file and directory operations. So right now, QFile and QDir and like QDir iterator and QFile info and all those classes, they do support file access, but it's all synchronous, right? So if you for instance do like listing a large directory, it will simply block. So you have to figure out like, okay, am I going to work with big directories? Maybe I need to put the whole thing into a separate thread just so that my UI doesn't block while I'm listing all the files. So I would like to have an API which will be inspired by QFile and QDir and QFile info, but it will be purely QCoro specific, and it will be purely using coroutines and probably some asynchronous methods or some asynchronous operating system APIs. Like on Windows, there's a great asynchronous API for file access. On Linux, there's now IOUring as well. So I would like to use those to make sure that to avoid those blocking syscalls, for instance, as well. And yeah, I'm always open to receiving more ideas, like what could be turned into a coroutine next. So that's that from me. Hope it made some sense to you. If you have any questions, I'm happy to answer them.
Thank you, Daniel, for your nice talk. There's one question in the Q&A. If you have more questions, please write your question down, and we will try to answer them here. After the Q&A, there will be a meet up in the lounge for track C. So you can interact with Daniel again. So the first question is my understanding is from Kai Song. My understanding is that when using this approach, the co-await needs to be in the top level function of the coroutine. If this is correct, what is your approach for more complicated examples where you would want to suspend a function called from the coroutine?
Well, the co-wait needs to be everywhere where you want to wait for a result of a coroutine. So if you have a coroutine that does something and you want its result, you have to co-wait it. And then likely your function will have some result that caller of your function will also want to consume. So the caller will have to co-wait on your function, and then this chains up to the point in the, for instance, event loop, which just ignores the result. It doesn't co-wait. I hope I understand that your question correctly, that if that's what you ask. You don't need to co-wait all the way up to the event loop. In theory, you could co-wait. You could decide not to co-wait a particular coroutine, but then you won't get the result of that coroutine, right? You will not be able to retrieve it. And I'm actually not sure if that would work well with QCoro if the caller gets terminated before all the nested coroutines are finished.
Yeah, usually the coroutine starts off in a suspended state or is suspended at any point where it awaits on something. Isn't it?
Well, QCoro actually, the way it's done is the coroutine gets, I think it gets resumed at the beginning automatically.
Okay. So I don't see any more questions. It seems the Twitter handle seems to be not correct on your sides.
Oh, do I have my own Twitter name wrong? Yeah, probably. Thank you.
There's a comment in the chat. Okay. What's your actual Twitter name then?
I suppose it's Vrátil then.
Okay, like your
like my GitHub handle, yeah.
Okay.
Is it though?
So.
See, I don't even know my own Twitter name.
Okay, thanks again, and let's meet in the lounge for track C, and then discuss coroutines with Qt if you want.
Thank you for your attention. See you in the lounge. Bye-bye.